Um, Hello there. My name is Joshua Katumba, and I'll be taking you through the assignment that we're given. My title reads A Machine Learning Architecture for Non-Evasive Dyslexia Screening via Behavior Telemetry under the Severe Class Imbalance. So, we're tasked to train two models, and I came up with two. The first one is called a cat boost, and the second one is called an extreme learning machine. So, with a cat boost, Um, it has decision trees behind it, and it's very effective with handling numerical and categorical features. This includes figures, of course, and then also the categories without doing a lot of preprocessing. Preprocessing is whereby you convert the data into structured format. So you don't need a lot of extensive preprocessing here. So it builds the model in a way that it's less prone to overfitting. Overfitting is whereby a model deeply memorizes the data to an extent whereby it also takes in the noise. So it can no longer separate what is actually the real data to predict and what is not. So this sometimes makes the model less reliable. And then it also has leveraging techniques like ordered boosting and semantic tree structure to manage the dataset's complexity. So the next one is called extreme learning machine. With this one, it is good with tabular data. That's the first thing. And the second thing is it's very fast. So the way it works is it maps its data or inputs into a highly dimensional hidden layer. Now that layer usually has neurons that analytically determine the outputs and weights, making it efficient for processing. So I'll go through the cat boost first. And I spoke about the decision trees. So with this one, it had a depth of 4. Then we had over 196 features from the data set. And then the trees were built sequentially. We're correcting the errors from the previous trees. So at the end, the model aggregated all the outputs from the numerous trees, come up with an actual prediction. Then we have the architecture. With the architecture, the first thing we did was to load the data. Then from there, we carried out some exploration. Then we looked for missing values. Afterwards, did some feature engineering to give the data more meaning. And then we looked at some processing. This one came in more to help us optimize the model so that we get a better prediction. Then we did data splitting, did an 80 to a 20 split. And after doing the splits, we came up with the first accuracy value. It's in my notebook. I never put it here, but that value wasn't enough. So what I did, I used another technique, one auditing technique to make the model much better. It's called hyperparameter tuning using a grid search CV. So here, I'm sorry for the noise, I can imagine. So here, we had training parameters where we did 200 iterations. Then we had a learning rate of 0.1, and the loss function we used was called a log loss. Then for the random seed, it was 42 and a verbose of 0. So hyperparameter tuning using grid search CV. This wasn't the only technique I used, by the way. I also used a cross-validation technique where I used k-folds, but instead I found out that the accuracy was again going lower. So I stuck to hyperparameter tuning using a grid search CV. Then the other one was I did also some advanced feature scaling, but it didn't really change the accuracy that much. So this was the best. So the primary technique applied to optimize this model was hyperparameter tuning. So using the grid search, it was able to search for optimal values for iteration, learning rates, and the depth. And since we are dealing with categorical and numerical data, it was very good for us. And the algorithm was able to make a much better prediction. Then the extreme learning machine, This one was recommended by Dr. Galiwango. Yeah, he told us that we should use this instead of any random forests. And for it, as I explained earlier, it maps the inputs onto a hidden layer. Now that layer can have over 100 neurons. So after doing that, it randomly assigns fixed weights, and the output then is computed to produce a binary classification which leverages the fixed high-dimensional hidden representation. So we had over 196 input features into the hidden layer of 100 units, and these input to hidden weights were fixed. So the hidden layer outputs are then used to analytically solve for the output layer weights using a pseudo-inverse calculation, bypassing iterative optimization steps completely for immense speed. So one of the advantages I spoke about in the beginning was this model is really fast, and I don't need to do very many iterations like the ones we saw in the cut boost. So it just goes through once. Now this is the architecture. We had data loading, we had data exploration, handling missing data, then we did some pre-processing, advanced feature scaling, sorry, feature engineering, then data splitting, and for validation, I used what we call an SMOTE. Yes, that was a cross validation, and then I came up with the final model. So with architecture hyperparameters, we had units of over 50. Then we had a sigmoid function. And during the training process, of course, we didn't use any iterative training hyperparameters like batch sizes, patience, since we're dealing with an ELM. Then it gave us a minority class score of 0.3349. Now, this was a technique I used, cross-validation. Initially, the model struggled severely with the minority class, showing a very low mean recall of 0.0264, and then the F1 score of 0.461 without imbalance to address this. And we applied an SMOTE, which is synthetic minority oversampling technique, in the K-fold cross-validation processes. So that technique helps with synthesizing new samples from the minority class, effectively balancing the training data in each fold. And the impact was significant because it improved from a 0.32 to a 0.58. And the metrics were here. So use the cut boost, and our accuracy was 0.89, which is 89%. But again, the ELM showed us that it was much better because it gave us a 0.90, which is 90% accuracy. So I'm so certain that in the coming assignments, we should probably use an ELM because it's more accurate, and it's even what was recommended to us to use. Thank you for listening. My drawing tools were cargo.com, sorry, draw.io. Then I used cargo.com, train the dataset, and Google Colab.